music. We previously discussed transformer vector groups and their impact on phase angles. Today, we focus on differential protection. Consider a 30 MVA transformer converting 115 kV to 34.5 kV. The high voltage current is 151 amps and the low voltage current is 503 amps. We mentioned internal connections of the transformer affect the phase shift angle of the voltages and affect current angles. We discussed the impact of these angles on differential protection and its resolution, so stay with us. Assume a 30 MVA transformer converting 115 kilovolts to 34.5 kilovolts. Thus, high voltage current is 151 amps and low voltage current is 503 amps, calculated on 115 kV side using power equation. Let's assume there is a 30 megavolt amp transformer that converts from 115 kilovolts to 34.5 kilovolts. Therefore, the high voltage rated current will be 151 amps, while the low voltage rated current will be 503 amps, as the rated current was calculated on the 115 kilovolt side using the aberrant power equation. 303 on bar, where the 115 kilovolt amperes were calculated from the ampere power equation. The current is 30 MVA divided by 3 times 115 kV, 151A. For the low voltage side, change 115 kV to 34.5 kV, 30 MVA, divided by 3 times 34.5 kV, 503A. P1 equals P2, power is equal. Higher voltage on the high side means lower current, and lower voltage on the low side means higher current. A city ratio was chosen, 200 to 5 for high voltage, and 600 to 5 for low voltage. From the basic theory of transformers, P1 equals P2, meaning that the power on the high voltage side is the same as the power on the low voltage side. Therefore, an increase in voltage on the high voltage side will be accompanied by a decrease in current on the high voltage side, while a decrease in voltage on the low voltage side will be accompanied by an increase in current on the low voltage side. Standard city ratios, 200 to 5 for high voltage, 600 to 5 for low voltage. 151A on high voltage side becomes 3.78A secondary. 303A on low voltage side becomes 4.19A. Calculations, 151A, 5, 200, wires 3.78A, 503A, 5, 600, 4.19A. Therefore, when converting the primary current of 151A on the high voltage side to the city secondary side, the current value will be 3.78A. Meanwhile, when converting the primary current of 503A, which is the current on the low voltage side of the transformer, to its city secondary side, the current value will be 4.119A. These values were found through ratio and proportion, where we ask ourselves this question. If 200 amps in the city ratio gives me 5 amps, how much will 151 amps give me? So we calculate it as follows. 151 amps multiplied by 5 divided by 200 equals 3.78 amps. Similarly, we say 503 amps multiplied by 5 divided by 600 gives me approximately 4.19 amps on the city secondary. Phase A's number. Phase A's value applies to B and C, differing only in angle. B is 120 degrees less, C is 120 degrees more. In a YY0 transformer, phase shift between high and low voltage is 0, so currents share phase angles. High voltage current at 151 amps, 0 angle, means low voltage is 503 amps. As for phase C, it will be plus 120 degrees relative to phase A as well. Since the vector group of this transformer is of type YY0, the phase shift or phase displacement between the high voltage and low voltage sides is 0. Therefore, the phase displacement between the high voltage and low voltage currents will also be 0, as these currents take the same phase angles. If the high voltage current is 151 amps at 0 angle, the low voltage current is 503 amps at 0 angle, the current's angle is affected by the load type. It lags if inductive, leads if capacitive, and aligns if resistive. Here, we discuss the phase displacement angle, the difference between high and low voltage sides, assuming negligible transformer inductance and an ideal transformer. In this YY0 transformer phasor diagram, high and low voltage currents align at 0 degrees, indicating 0 phase shift. Regarding the voltages, if the load is of a resistive type, we are talking in this case about the phase displacement angle, not the angle of the current itself, but rather the difference in angle between the high voltage side and the low voltage side, assuming that the inductance of the transformer is negligible and that this transformer is an ideal transformer. In YY0 transformers, notice how high and low voltage currents align, indicating zero phase shift. If the city star point is chosen similarly for all cities with high voltage directed towards and low voltage away from the transformer, the relay won't issue a trip signal under normal conditions. Differential protection combines both currents, finding no angle difference. Therefore, city location must be chosen carefully. For this reason, if the current transformer aggregation point, also known as the city star point, is chosen similarly for all the cities at the transformer terminals, meaning selecting the city star point on the high voltage side to be directed towards the transformer, and choosing the city star point on the low voltage side to be away from the transformer, it means that the relay will not see the transformer to issue a trip signal under normal conditions. Differential protection combines high and low voltage currents, finding a trip signal as both have a zero angle. Choose the city star point for CTs at equipment terminals, directing them towards the transformer, or position CTs star points away to. The star point for all the CTs at the terminals of the equipment in differential protection should be directed towards the part that needs protection or the equipment that needs to be protected, which in our case is the transformer. Alternatively, all the CT's star points can be positioned away from the equipment to be protected, so that we create two currents going to the relay, one at a zero angle and the other at a 180-degree angle under normal conditions. This way, the sum of the directions going to the differential will be zero. Reverse stability by directing B2 of all CTs to the equipment needing protection, connecting S1 to the relay, and making S2 the city star point. If P2 of the first CT and P1 of the second CT face the protected part, connect S1 of the first and S2 of the second to the relay. If CT swapping isn't possible, adjust via software. If we find that the CT is installed so that P1 is the one towards the protected part, then S2 must be connected to the relay for all CTs, and then the CT starburg must be on S1. However, if we find that the direction of P2 for the first CT is towards the protected part, while the direction of P1 for the second CT is towards the protected part, then S1 must be connected to the first CT, to the relay, and connect S2 of the second CT to the relay to maintain the stability of the differential protection. If it's not possible to make hardware adjustments like CT swapping, it can be done through the relay software without any external modifications. The inspiration for the revival of a nation when mentioning the phase shift angle for the current on the transformer's terminals in simulation programs is 180 degrees as shown in this image. This refers to the values displayed on the relay and connected to it through the city secondary, not the actual values or angles of the currents. Now let's return to the previous example once again. So, when converting 151 amps to its city secondary, the current value will be 3.78. When converting a current value of 503 amps to the city secondary, it will be 4.19 at an angle of 180 degrees. This is because we have reversed the polarity, and both currents will meet at the differential protection. So the differential protection will calculate the value of the differential current, being their vector sum, while it calculates the restraint current, being their algebraic sum divided by 2. Thus, the I differential or I operated will equal 3.78 plus 4.19 at an angle of 180 degrees, which equals 0.4 amps. The restraint will be 3.78 plus 4.19 divided by 2 equals 3.98 amps. So we find that the ratio of the differential current to the restraint current is 10%. 78 at 0 plus 4 put on 9. The 180 degrees equals amps. As for the aristyrene, it will be 3.78 as an algebraic sum plus 4.19 over 2 and will equal 3.98 amperes. Thus, we will find that under normal conditions, the differential current ratio of the aristyrene current is 10%. Winding stability minimizes current differences. With 3.8 amps on winding 1 and 4.2 amps on winding 2, differential current changes from 0.4 to 0.01 amps and strain current from 3.98 to 1 amp. This applies to YY0 transformers, but not all transformers share this vector group. For DY or YD transformers, high and low voltage rated currents are both 151 amps for high voltage and 503 amps for low voltage. The difference is in line current. In star connection, line equals phase current. In delta, phase equals line divided by 3. The explanation so far is for YY0 transformers, but not all transformers use this vector group. What if we use DY or YD? The rated current for high and low voltage is calculated as before. High voltage is 151 amps, low voltage is 503 amps. The difference is the line. Rated current is calculated. High voltage 151 amps, low voltage 503 amps. The current calculated is line current. Line equals phase current in star. Phase equals line divided by 3 in delta. In star, high voltage line to neutral equals line to line 151 amps. In delta, low voltage line to neutral equals line to line divided by 3, about 291 amps. Vector group YND1 means low voltage in delta is delayed by 30 degrees compared to high voltage in star. Therefore, the high voltage line to neutral in the star connection is the same as the line to line and equals 151 amps, while the low voltage line to neutral in the delta connection will equal the low voltage line to line divided by the square root of 3, which equals 503 amps divided by the square root of 3, approximately 291 amps. This vector group is of type YND1, which means that the low voltage on the delta side will be 30 degrees behind the high voltage on the star side, and this also applies to the primary current. That is, if we assume that the direction of the current is 151 amps at an angle of 0, then the direction of the delta will be 503 amps at an angle of minus 30 degrees, and the angle can be described as either minus 30 degrees or 330 degrees. Notice with me in this phasor diagram of the Y-delta transformer how the line currents in the delta are delayed by 30 degrees compared to the line currents in the star. Now, when converting the current value of 151 amps at an angle of 0 to its city secondary, the current value on the city secondary will be 3.78 amps at an angle of 0. If we take the reading from S1, it will be 3.78 at 180 degrees if we take the reading from S2. Converting 503 amps at 30 degrees to city secondary, the current is 4.19 amps at 30 degrees from S2 and 4.19 amps at 150 degrees from S1. This 150 degrees results from 180 minus 30 due to polarity reversal and vector group. B2 direction for all CTs is towards the transformer, so S1 connects to the relay, linking 3.78 at 0 degrees and 4.19 at 150 degrees. To minimize current differences, we use winding stop, 3.8 amps on winding 1 and 4.2 amps on winding 2. After adjustments, the value is 0.99 at 0 degrees, corresponding to 1 amp at 150 degrees, meeting at the differential relay. B2 is directed towards the transformer. Connect S1 to the relay. Use winding stop, 3.8 amps on winding 1, 4.2 amps on winding 2. A differential current remains due to angle imbalance, 0 degrees on high voltage, 150 degrees on low, instead of 180 degrees. Minimize current differences with winding stop, 3.8 amps on winding 1, 4.2 amps on winding 2. Post adjustment, 0.99 at 0 degrees meets 1 amp at 150 degrees at the relay. Problem, differential current persists due to angle imbalance. High voltage is 0 degrees, low voltage is 150 degrees, needing 180 degrees to cancel. Differential current, sum of 0.99 at 0 degrees and 1 amp at 150 degrees is 0.4 amps. Adjust angles to balance the system, making differential current 0 degrees by adding 30 degrees to 150 degrees to reach 180 degrees. We will encounter a new problem. Even after adjusting the current values, a differential current will appear due to the imbalance of angles on both sides, where the angle of the current on the high voltage side is 0, while the angle of the current on the low voltage side is 150 degrees, whereas it should be 180 degrees to cancel out the other side. Notice that the value of the differential current, which is the vector sum of 0.99 at an angle of 0 plus 1 amp at an angle of 150 degrees, will give me 0.4 amps. Here, we need to adjust the angle values to balance the system under normal conditions, making the differential current at an angle of 0. This is done by adding 30 degrees to 150 degrees to make it 180 degrees, while keeping the 0 degrees on the high voltage side as it is. The 0 degrees on the high voltage side remain as they are, and this is called phase shift compensation. The purpose of this phase shift compensation is to adjust the angle values regardless of the type of vector group used, so that the phase shift between both currents is 180 degrees, allowing one to cancel the other out easily. We notice that after adjusting the angle values, the differential current value has become very small, which is what is required under normal conditions. Thus the value, after adjusting the angles, is the vector sum of 0.99 at an angle of 0, plus 1 amp at an angle of 180 degrees, which equals 0.01 amps. Notice with me, To achieve stability on the vector group YD1, I need to control 6 currents. 3 currents at 0 degrees, and the angle between them is minus 120 degrees, and plus 120 degrees from the phase A ratio. This means that we need to inject 3 currents at an angle of 0, at an angle of negative 120 degrees, at an angle of positive 120 degrees. Inject 3 currents into Y2 phase A at 150 degrees. For phase B, inject at 30 degrees. For phase C, inject at 270 degrees. Connect 6 currents from the injection device to the transformer differential relay. Inject calculated values from both sides, converted and multiplied by a factor with distinct values for each side. For phase C, we inject a current at 270 degrees, which is also negative 90 degrees. This diagram shows how to connect the 6 currents from the injection device to the transformer differential relay. Take the output contact as feedback to the device. To achieve stability for the transformer's differential protection, inject the calculated current values on both sides of the transformer after conversion and multiplication by a factor. This factor is found by dividing one value by another with distinct values for each side. The stability for the differential protection of the transformer is the value that has been found or calculated on both sides of the transformer, but after converting it through a certain process and then multiplying it, which is known as a factor. The value of this factor can be found by dividing one value by another, and of course it will have 2 values, one value for one side and another value for the other side. And Kim on the ruble tasting and Kim on the ruble tasting. If you want to achieve stability for single-phase transformer differential protection, the process is different. You need to convert the rated current value to the city secondary, then multiply it by the city correction factor, and then multiply it by the vector group factor. Then multiply it by the vector group factor. In some relays, the symbol KVG represents a factor whose value depends on the adjacent number's parity. If odd, the factor is 3. If even, it's 1.5. Older electromechanical relays manage transformer vector group differences by altering CT connections. Delta side CTs were star configured and star side CTs were delta configured, achieving phase shift through wiring. For a DY1 vector group, CTs were connected in a YND11 configuration. Microprocessor relays perform this internally, without external connections. In this way, we have achieved phase shift communication, but through the wiring connection. If the vector group is of type DY1, we connect the CTs in a YND11 configuration. This is actually done in exactly the same way in microprocessor relays, but it is done internally without adding any external connections. To clarify this image, let's take this new example. If I have a transformer with a vector group of YD1, the high voltage rated current is 251 amps, and the low voltage rated current is 502 amps. Therefore, we connect the CTs on the high voltage side, which is the delta side, in a star configuration, and we connect the CTs on the low voltage side, which is the star side, in a delta configuration. Now we convert primary current on the high voltage side, which is 251 amps at an angle of 0, to the CT secondary. This will give me 4.18 amps at an angle of 0 as well. As for the low voltage rated current, its value is 502 amps at an angle of negative 30 degrees. This negative 30 degrees, as we mentioned, is due to the vector group DY1. Therefore, if we connect CTs in a delta configuration, this 30 degrees will return to us after the current rotates counterclockwise by 30 degrees. Therefore, the value that will appear on the Alexandrian 6 connected in the form of a delta will be 4.35 amps at an angle of 0, as it was minus 30 degrees in the barrels, and in the Alexandrian it became plus 30 degrees, so the total became 0. The current exits the transformer, reversing polarity on the secondary side to stabilize the differential relay at 180 degrees. By balancing angle and current values using tap settings, both currents entering the relay equal 1 per unit. Using YND1, we adjusted current values with the Wyoming tab and different connections to achieve a 180-degree phase angle difference across all phases. Calculations for I restrain and I operating current show relay stability when normal current flows It's 1 per unit at 0 degrees matching 1 per unit at 180 degrees. Analyze this YND1 example if you have time. We use the Wyoming tab to adjust currents. How did the phase angle difference reach 180 degrees? This table shows I restrain and I operating current calculations for 3 phases, indicating the relay stays stable with normal current as I operating current is near 0. In another scenario challenging the transformer differential protection relay, DPR, an external earth fault creates a closed path through the transformer's grounded star, causing false DPR activation. Phase angle difference reaches 180 degrees between currents. Relay stays stable with normal current as I operating current is near 0. An earth fault outside transformer boundaries causes a closed path through the transformer's grounded star, leading to false DPR activation. Assume an earth fault on the red phase. Fault current on the low voltage side is 3 per unit on the red phase, 0 on yellow and blue. The other scenario that poses a challenge for the transformer differential protection relay, DPR, is the occurrence of an earth fault outside the transformer boundaries. It has been found that the earth fault current will create a closed path through the grounded star of the transformer. This earth fault will cause the DPR to activate, leading to a false operation of the DPR in the case of an external earth fault. To clarify the concepts better, let's assume that an earth fault occurred on the red phase, as shown in this image. We will notice that the fault current on the low voltage side will be 3 per unit on the phase where the fault occurred, which is the red phase, and 0 on the yellow and 0 on the blue. The fault current will reflect on the high voltage side across the 3 phases in a ratio of 2:1:1, where there will be a positive 2 on the same phase corresponding to the phase where the fault occurred, and -1 on the yellow phase and -1 on the blue phase. Therefore, the value of the differential current is the absolute value resulting from subtracting both currents, which is positive 2 minus 1 minus 1, resulting in positive 3, 0, 0. The result will be positive 1 for the red, yellow, and blue phases. These values are before. This can cause a false operation of the differential relay, and this issue can be resolved by removing the zero sequence current value from the differential current calculations to maintain the stability of the differential current at the moment of an external earth fault. This is known as zero sequence elimination. By God. So, if we calculate the zero sequence current using I0 or 1/3 sum of phase currents, then I secondary dash is used in differential calculations, relay factors, 1, CT ratio correction, 2, phase angle combination, 3, vector group factor, 4, zero sequence elimination. The sum of currents from the 3 low voltage phases where the fault occurred is called I secondary dash. It's crucial for relay stability during faults. Relay combination factors for transformer protection include CT ratio correction, phase angle combination, vector group factor, and zero sequence elimination. The table summarizes phase combination and zero sequence filtering based on vector group type. For a lagging angle of 30 degrees, add plus 30 degrees. For a leading angle of plus 30 degrees, add 30 degrees. The table also shows factors for current injection into the relay for 3-phase, 2-phase, and single-phase faults. For single-phase faults, determine zero sequence activation as it affects factor values. Phase combinations and zero sequence filtering depend on vector group type. For a lagging angle of 30 degrees, add plus 30 degrees. For a leading angle of plus 30 degrees, subtract 30 degrees. Zero sequence filtering occurs where the winding connects to the ground or any terminal passing zero sequence. Factors to multiply by the current injected into. Or any terminal that can pass zero sequence through it has zero sequence filtering. This table summarizes the factors that we need to multiply by the current that we will inject into the relay in the case of 3-phase, 2-phase, and single-phase faults. In the case of single-phase faults, it is important to determine whether the zero sequence is activated or not, as this will also affect the value of these factors. Differential current is the product of differential current setting, I-rated current, and KVG. KVG factor varies with fault type, 3-phase, 2-phase, single-phase, vector group type, odd-even, and zero sequence elimination status. Matrix pairs are selected based on the transformer's vector group for side compensation. For vector group PYN1, matrix 1 is for the star side, matrix 0 for the delta side, with delta as reference. Each factor is multiplied by its respective current values. Matrix pairs are selected based on the transformer's vector group type for compensation. For PN1, choose matrix 1 for star, 0 for delta. DY1 causes 30-degree lag on star. Matrix 1 results in 1 amp at plus 30 degrees, offsetting 30 degrees. If we assume that there is a transformer with a vector group of PIN1, we choose matrix number 1 for the star side and matrix number 0 for the delta side, considering that the delta side is always the reference. Therefore, we multiply each combination factor by its respective current values on each side. As we told you before, the DYN1 will make the current lag by minus 30 degrees on the curtain side. When choosing the curtain side matrix number 1, we will notice that after compensating the matrix, the expected current value will be 1 ampere at an angle of plus 30 degrees until we compensate for the minus 30 degrees, so the final sum becomes 0. To set differential protection in transformers, use the vector group on the nameplate. This method can cause errors because it assumes an ABC phase rotation and specific phase connections. Even if these are met, the nameplate ignores external factors like city connection type, polarity, and relay input connection. Consider these factors and follow the relay manual when selecting the vector group. The first condition is that the system represents an ABC phase rotation, while the second condition assumes that phase A is connected to H1 and X1 pushing, phase B is connected to H2 and X2 pushing, and phase C is connected to H3 and X3 pushing. Even if we assume that both conditions have been met, the transformer nameplate still does not take into account external factors that may affect the phase shift perceived by the relay. These external factors include the city connection, whether it is star or delta, in addition to the city polarity direction, and finally, the relay current input connection. Therefore, when selecting the vector group indicated on the transformer nameplate, we must take into account all external factors and the correct connection conditions mentioned in the relay manual literally. The mind initially exchanges that the vector group for this connection is DYN1, which is the vector group mentioned in the transformer of the sum. And accordingly, we choose the matrix number 1 towards the star and the matrix number 0 towards the delta, where the delta is always the reference, and accordingly we choose the pair of matrices 0 and 1. When compensating the value of the compensation factor to the values of the currents on the low voltage side or the star side, we will notice that after compensating the matrix, the value of the resulting current will appear as 1 ampere at an angle of plus 30 degrees. But when focusing on the path of connecting the phases with the bushing and taking it into consideration, we will find that phase A is connected to H3 and not H1, and phase B is connected to H2, and phase C it is connected to, and this means that the connection has been reversed, and therefore, in this case, it becomes, instead of what was mentioned, so in this case, the vector group becomes, it is not mentioned in the transfer from Blair. The matrices in the transformer differential relay should be 0 and 11, not 0 and 1. Matrices 0 and 11 provide an angle compensation of minus 30 degrees, balancing the existing plus 30 degrees, resulting in a net direction of 0, which is desired. Conversely, matrices 0 and 1 result in a total of 60 degrees, which is incorrect. An engineer might ask, with a transformer vector group of DYN1, can I choose either side as the reference for angles or the reference windings? Essentially, can I set winding 1 to 0 and winding 2 to 1, or winding 1 to 11 and winding 2 to 12, as long as the phase shift and minus 30 degrees are maintained? If I have a transformer with a vector group of DYN1, do I have complete freedom to choose either side of the transformer as a reference for the angles, or what is known as the reference windings? In other words, can I choose winding 1 to be 0 and winding 2 to be 1, or choose winding 1 to be 11 and winding 2 to be 12, as long as I maintain the phase shift and the minus 30 degrees? One of the common misconceptions in many electrical stations related to differential protection of transformers in general, and specifically regarding the SEL protection devices, is that you have complete freedom to choose either side of the transformer as a reference for the angles when determining the compensation matrices. This could lead to the reference being chosen arbitrarily. It varies from relay to relay and is closely related to the way the bias current is calculated. The goal we aim for is to ensure increased stability of the protection devices with external interference between the phases so that the bias current value does not drop to zero at the moment of a fault. Therefore, any small value of the differential current for any reason will cause the relay to issue a false tripping signal. Additionally, this selection impacts relay sensitivity to transformer internal ground faults. Fault records show incorrect matrix pair choices can misoperate differential protection in rare faults. Comparing matrix pairs 11 and 12 with 0 and 1 showed more stability with 0 and 1. For relay safety, use the delta side as an angle reference to avoid even-numbered matrices like 2, 4, 6, 8, 12, which may cause incorrect tripping. An external fault activated differential protection due to matrix pair 11 and 12. Simulating and comparing matrix pairs 11, 12 with 0, 1 showed lower value, more stability with 0, 1. For safety, select matrix pairs for relays. 1, use delta side as angle reference. Avoid even-numbered matrices like 2, 4, 6, 8, 12, etc. to prevent incorrect relay trips, especially in phase faults or faults with equal currents on two phases. 180-degree shift. Specific to current relays, AB relays use star connection for angles. It is more stable when the combination is 0 and 1. To enhance safety, choose the delta side as the angle reference to avoid even-numbered matrices like 2, 4, 6, 8, 12, etc., which may cause incorrect relay trips. This is specific to current relays, as AB relays use the star connection for angles. For zigzag transformers with the delta side in the protection zone, use matrix 12 to eliminate zero-sequence current during external faults, especially in cases of faults between phases or create two equal currents on two phases with a 180-degree phase shift. The AB relay uses the star connection as the angle reference. When using a zigzag transformer with the delta side in the differential protection zone, use matrix 12 on the delta side to eliminate zero-sequence current during external ground faults, preventing correct differential relay operation. Using a zigzag transformer in the differential protection zone, use matrix 12 on the delta side to eliminate zero-sequence current during external ground faults, preventing incorrect relay operation. For example, with a vector group DYN1 transformer. With a zigzag transformer on the delta side, use matrix pairs 12 and 1 instead of 0 and 1. For auto transformers, choose matrix pair 11 and 11 instead of 12 and 12 for the same reasons. Choose matrix pair 0 and 0 if not using zero-sequence elimination. For him as well. If there is a zigzag transformer connected to the delta side, we use the matrix pairs 12 and 1 instead of using the matrix pairs 0 and 1. In the case of using auto transformers, we should choose the matrix pair to be 11 and 11 instead of 12 and 12 for the same previous reasons. We can also choose the matrix pairs 0 and 0 if we do not wish to use zero-sequence elimination. For more details on this topic, you can read the attached files with this episode, which include a scientific article from SEL, as well as a seminar from Hitachi, or the former LB. Now, let's take a practical example that summarizes most of what has been mentioned in this episode. If there is a transformer with a capacity of 750 megavolt amperes that converts from 500 kilovolts to 220 kilovolts, and its vector group is Y0, the high voltage city ratio is 1250 to 1, and the low voltage city ratio is 2500 to 1. And the low voltage city ratio is 2500 to 1. Which of the following is best? 1. Rated current on both ends of the transformer. 2. City ratio correction on both sides of the transformer. 3. Three-phase, two-phase, single-phase, primary. 66A at 500 kV. Low 1968A at 220 kV. Secondary 0.692A. The rated current on the primary side will be 750 megavolt amperes divided by the square root of 3 times 500 kilovolts, which equals 866 amperes. As for any rated current, on the low voltage side, it will be 750 megavolt amperes divided by the square root of 3 at 220 kilovolts, which equals 1968 amperes. Now let's calculate the current value on the secondary side for each side. We say 866 amperes divided by the specific ratio, which is 1250 to 1, equals 0.692 amperes. 1.692, a primary, secondary, YY0. The secondary current is 1968 amperes. The transformer vector group has a vector group factor of 1 for 3 and 2-phase faults and 1.5 for single-phase fault. For stability in transformer differential protection relay, apply a 180-degree phase shift crucial for all three phases. The vector group factor is 1 for 3-phase and 2-phase faults, and 1.5 for single-phase faults if zero sequence elimination is activated. To stabilize the transformer differential protection relay, inject 6 currents with a 180-degree phase shift. This shift must be applied to all 3 phases, between corresponding high and low voltage sides. Injecting these currents results in relay readings showing rated current on both transformer sides, with the differential current at 0 under normal conditions, and the string current at 2 per unit, as it sums on K. The most important thing to focus on is that the phase shift is 180 degrees, and it doesn't matter where we place the 180 degrees, whether on the high voltage side or the low voltage side. It is crucial that the phase shift of 180 degrees must be applied to all 3 phases together, between the red phase on the high voltage side and its corresponding red phase on the low voltage side, as well as the yellow with yellow and blue with blue. Injecting 6 currents into the relay. Rated current is injected on both sides, seen as 1 per unit on city secondary. Differential current is 0 normally. String current is 2 per unit, sum on K. The K factor equals 1. Red phase at 0 angle on both sides. Differential and strain currents are 2. For stability with external 2-phase load L1, L2, inject values, angles as diagram shows. 180-degree phase shift between high-low voltage sides and L1, L2 same side. The symbol K equals 1. Injecting the red phase at 0 degrees results in a differential and strain current of 2. For stability with a 2-phase load between L1 and L2, inject values as shown. The 180-degree phase shift occurs between voltage sides and L1, L2. Differential current must be 0. Restraint current 2 on 2 phases. For single-phase load stability, assuming L1, injection history varies by grounding. If the source is isolated and the other side grounded, activate zero sequence elimination on the grounded side, calculate zero sequence current, 1/3 of the vector sum, and subtract from phase currents. In this case, the differential current should remain 0, while the restraint current equals 2 on 2 phases. For stability with an external single-phase load, assuming L1, the injection history varies by grounding method. If the source side is isolated and the other side grounded, activate zero sequence elimination on the grounded side. Calculate the zero sequence current as 1/3 of the vector sum of the 3 currents, then subtract from each phase's current. Inject these into the relay. Differential current equals 1 on the fault phase, 0.5 on others. Restraint current equals 2 on the fault phase, 1 on others. When a ground fault occurs on the grounded star side, the other side, star or delta, has a fault ratio of 2-1-1. If both sides are grounded, activate zero sequence elimination for winding 1 and 2. When we inject these values and angles into the relay, we will notice that the differential current will equal 1 on the phase where the fault occurred and will equal 0.5 on the other phases, while the restraint current will equal 2 on the phase where the fault occurred and will equal 1 on the other phases. Notice in this image that when a ground fault occurs on the grounded star side of the transformer, the other side, whether it is a star or delta, will have a fault ratio of 2-1-1. If the transformer is grounded on both sides, then zero sequence elimination will be activated or set to on for winding 1 and winding 2. Multiply the values for the 3-phase or 2-phase fault by the KVG factor of 1.5. Inject the result with a 180-degree phase shift. The high voltage side value will differ from the low voltage side. If the transformer is ungrounded or not activated on both sides, do not multiply by 1.5. Inject the same values as in the 3-phase or 2-phase case on one phase with a 180-degree phase shift. Test differential current settings and tripping characteristics, e.g. a setting value of 0.2. Value 0. Except one injected phase 2, if not grounded or activated. Both sides treated differently. No 1.5 multiplication. Inject same values. 3 part 2 phase 1 phase, 180-degree phase shift HVLV. This differential stability test. Differential sensitivity test involves testing current settings, tripping characteristics. If setting 0.2, test HV side faults. 0.2 times rated current, ICT ratio, equals 0.13. Therefore, I inject the same values used in the case of a 3-phase or 2-phase fault on only one phase with a phase shift of 180 degrees between the high voltage and low voltage. What has been mentioned is called the differential secondary stability test. As for the differential secondary sensitivity test, it is done by testing the differential current setting values and checking its tripping characteristics. For example, if the differential current setting value equals 0.2, so, when testing the differential current setting on the high voltage side for a 3-phase or 2-phase fault, I need to calculate the value of 0.2 multiplied by the rated current on the high voltage side divided by the ICT ratio. This will equal 0.2 times 866 divided by 1250 to 1, which equals 0.13. Value is 0.166 on 1 to 4 equals 0.1. Inject 0.1 times low voltage current on city ratio. 0.2 times 1968, 2500 equals 0.157A. Inject 3-phase current on low voltage. So, we inject a current at a value of 0.1 multiplied by the low voltage rated current on the city ratio present on the low voltage side. So, 0.2 will be multiplied by 1968 divided by 2500, which equals 0.157 amperes. This means that if I inject a 3-phase current on the low voltage side gradually from 0 without injecting any current on the high voltage side, the differential relay will operate at a value of 0.157 amperes. Test injecting only. Gradually inject current to 0.207 for 0.2 differential on high voltage. For low voltage, inject from 0 to 0.236A to trip. Test 0.2 differential current. Inject 0.207A for high voltage, 236A for low voltage single phase. If zero sequence elimination is off, multiply by 1. Use relay's Excel sheet, understand equations. Therefore, I need to inject current gradually until we reach the value of 0.207 to test the 0.2 differential current setting on the high voltage side. If I want to test the 0.2 differential current setting on the low voltage side of the transformer in the case of single phase only, I gradually inject current from 0 up to a value of 0.236A, and at that point it should trigger a trip signal. If zero sequence elimination isn't activated, multiply by 1, not 1.5, yielding the same result as 3, or 2-phase. Each relay has an Excel sheet for calculations. Know how to use it to avoid errors. For testing transformer differential protection, calculate differential and restraint currents using equations from episode 6 to 8. Multiply the differential current by today's lecture factors for testing. For differential protection tests, use the calculated value as is when it equals 1. The value from previous equations is, what values should I inject? As for testing the tripping characteristics of the differential protection for transformers, we then calculate the differential current and the restraint current using the equations detailed in episodes 6, 7, and 8. The final result for calculating the differential current value is multiplied by the factors explained in today's lecture if you want to test the differential protection for transformers. Then, if we present the differential protection test and the lines, there are no factors to consider based on the value calculated previously, and we use the value as it is when the value equals 1. The value calculated from the previous equations is, here we will ask ourselves the question, what values should I inject on, and where is the winding? Where did you put the winding to? In order to produce a value, we are faced with two equations. What we will derive from these equations is that any change in one value will directly affect both of my values, the differential current and the restraint current. Therefore, in this case, it is not possible to fix the restraint current at 1 to achieve a differential current value of 0.25 unless we fix the magnitude and only change the angle. By solving the two equations together, we can predict the values that need to be injected into the relay to achieve the required values. If we take a value from one equation, then that value will equal, when we substitute one equation into the other, we will be able to find the differential current, and the restraint current cannot, in this case, fix the value of the restraint current at 1 to achieve a differential current value of 0.25 unless we fix the magnitude. Only change the angle. By solving the two equations together, we can predict the values that need to be injected into the relay to achieve the required values. If we take a value from one equation, then that value will equal, when we substitute one equation into the other, we will be able to find, if we take the value of the high voltage current from the differential current equation, then the value of the high voltage will equal, the high voltage current equals the low voltage current plus. So, when we substitute the high voltage current equation into the restraint current equation, we can find the low voltage current. After finding a value, we can determine another value by substituting into any of the previous equations. Notice with me that it equals 1 and equals plus. Now we substitute the equation that equals into the equation I love voltage. Now we substitute the equation that equals plus in the equation. So then it will equal 1, and it will equal 1 plus 2, I low voltage, and thus plus 2 I low voltage. Therefore, I low voltage will equal 1 minus, I low voltage will equal 1 minus 0.5, which will equal 0.5. And it will equal amperes times amperes. We substitute I low voltage current into I restrained to find I high voltage, where I high voltage will equal 1, which is bias current minus 0.375, which is I low voltage, resulting in 0.625A. Simply by adding and subtracting the two equations for differential and restrained current to find expected current values for the relay, adding I differential and I restraint, I differential plus I restraint will equal 2, I high voltage, where I low voltage corresponds. Thus, expected I high voltage for the relay equals I differential plus I restraint or I bias over 2 I restraint or 2. So, when we add the two equations, the I differential current and the I restraint current, we find that I differential plus I restraint will equal to I high voltage, where I low voltage corresponds to each other. Therefore, the expected I high voltage to be injected into the relay will equal I differential plus I restraint or I bias divided by 2. I restrain or 2. When we subtract the two equations, the differential and the restrained currents, we find that I differential minus I restrained will equal minus 2 I low voltage, where I high voltage corresponds to each other. Therefore, I low voltage will equal I restrained or I bias minus I differential divided by 2. If the value equals 1, then the value at which it should operate will equal according to, therefore, the expected value will be, and it will equal, the expected high voltage is 1 plus 0.25 divided by 2, equaling 0.625 amperes. The relay's expected current matches this. Before injecting currents, adjust values per previous calculations and this equation. We aim to adjust to 0.375. Adjust through the city factor as calculated before per this equation. Refer to the document for these calculations. In conclusion, when injecting a current of a certain value, we need to adjust to 0.375 before injecting currents. Adjust values through the city factor as calculated by this equation. Calculations for these values are in the document for reference. In conclusion, injecting a current will result in 0.433. And these calculations to find the values are also available in the same document. Thus, injecting current at 0.433 at 0 degrees and 0.295 at 180 degrees generates a differential current of 0.25 and a restraint current of 1 and minus 0.433, 3.433 at an angle of 0 on the high voltage side and injecting a current of 0.295 at an angle of 180 degrees on the low voltage side, we will have a differential current of 0.25 and a restraint current of 1. Test point 1, inject 0.433A at 0 degree high, restraint point equal to 1, differential current of 0.25. We inject a current on the high voltage side of 0.433 at an angle of 0 degrees and a current on the voltage side above 0.295 at an angle of 180 degrees. It's 0.320 and then gradually reduce the value of 0.320. Note the relay issues a retrip signal when the current value reaches exactly 0.295. The restraint current will equal 1 and the differential current will equal 0.25. So the relay has operated correctly according to the curve. 3, you want to taste, Gen 2, 0, 10, 3, J1, huh? So we notice that the relay should issue a retrip signal when the current value reaches exactly 0.295, and then we will notice that the restraint current value will equal 1 and the differential current value will equal 0.25, and this means that the relay worked according to the curve correctly. And that will be enough for today's lecture, and thank God, the Lord of the worlds. Stay tuned for the next episode where we will explain the details of low impedance differential protection. See you soon. We'll meet you on the measurement. How are you?